So for a quick rundown of the agenda, we'll start by talking about modernization, intelligent scaling, and infrastructure selection. And then we'll look at why visibility of your cost is so important with monitoring, going beyond single cluster into multi-cluster scheduling, tips around there for cost, and then we'll expand beyond Kubernetes into the broader Azure ecosystem. So organizations of many sizes, big or small, can be using containers. If you're a cloud native company, if you're looking to modernize your applications, containers are a great way to go. Gartner has actually projected that more than 90% of global organizations will be running containerized applications in production by 2027. So this is a huge amount of growth we've seen in the past couple of years that we'll continue to see in the years moving forward. There are many benefits of adopting Kubernetes, self-managed, or also AKS, a managed Kubernetes service. Primarily scalability, scaling your applications in and out based on your workload needs, automation and health. If your application goes down, for example, it can be re-provisioned, rescheduled in an automated fashion. And bin packing also helps you share resources across different workloads, whether it's owned by different teams or for different projects within your development scenarios. This really helps reduce your infrastructure costs. And from a managed Kubernetes standpoint, AKS helps automate a lot of this for you. You don't have to worry about this. The control plane is free for dev and test clusters. And when we think about cost, we also have to consider the people cost. So how much time and money are you spending to train folks to select the right infrastructure for your workload? This is an additional cost that you'll have to factor in as well. So time is money, and AKS can help you automate some of this. In the cloud world, we see that over-provisioning is big challenge. It can cause a lot of underutilization of your resources. In general, if you're bin packing efficiently, you should be able to hit 80 to 90% resource utilization, but this is not actually what we see across industry. Typically, it's a lot lower, around even 10% utilization sometimes for CPU, which is very, very low. This is from a Datadog report. Basically, how we interpret this is about 65% of workloads are being underutilized from both a CPU and memory perspective. So there's a really big opportunity for us to do better here and right size. So first, Karthik will be chatting a little bit about scaling.
Hey, good afternoon, everyone. Welcome back from lunch. I can say that scaling is a good topic after lunch. We'll find out. So I have a demo to showcase right-sizing and bin packing. It brings some of the greater aspects that we have on offer, including KEDA NAP. Some of you might have heard about node auto-provisioning that just went preview a while back, and vertical pod autoscaler. So before we get into the meat of the demo, I just want to showcase, we have seen what the different Copilot features are in Azure portal. So we'll quickly bring some prompts along to see what it spits out in terms of certain important questions for scalers. Oh yeah, sure. So we'll start off with Copilot, just to bring some prompts along and see for some common questions around scalers, how it answers in using Azure portal Copilot. In the demo, I'll be switching between VS Code editor using Azure CLI. You saw some Aritra showcase some of our Grafana charts. So I'll be using that with Azure Managed Prometheus. There's also some load testing behind the scenes that you will see in the Grafana charts. It's not really shown, but you can see it in action as we introduce a bursty traffic to go along with the scaling demo. So with that, let me see. Let me switch to the demo. So I'll be asking like 3 questions on Copilot. One, in terms of what is the best event-driven scaling option that's available in AKS. So it provides things around KEDA, differentiation between HPA and VPA, and then we'll round it off with, if it can provide information around node auto provisioning preview. So on the event-driven scaling, so KEDA comes with several 50+ scalars. You can scale down to 0, thereby saving in terms of resource utilization and cost, as well as carbon emission, which is big. And in terms of differentiation between VPA and HPA, and many of you know that HPA, you can monitor your memory, CPU metrics, and you can increase and decrease the pods, replicas. And in terms of VPA, it is about adjusting the pod container request and limits so that you do the right sizing properly. So VPA is useful for fluctuating workloads in that regards, for adjusting the deployment requests and limits. So all that is coming along in terms of docs. And then about node auto provisioning, which just went preview a while back. It will tell us that it's based out of the open source managed Carpenter project and how to enable it and some of the benefits in terms of cost effective SKUs, and it's meant to provide you the right sizing that you need in terms of VM size. So next we will move to creating a cluster that has KEDA, NAP, and VPA enabled. So I'll switch to VS Code. So here I'm creating a cluster with VPA, KEDA, and NAP enabled. We move to the deployment. It is pretty much a deployment that loads a lot of random strings in local memory. You can see that the request size is about 0.1 vCPU cores and about 50 megabytes of memory that is requested here. That will be useful as we come to the VPA definition next. This is a vertical pod autoscaler. So as I mentioned, the minimum allowed limit starts with what we specified in the original deployment, which is about 0.1 vCPU and 50 megabytes of memory. And then it can go up to 4 vCPUs and 500 megabytes. We specify an ingress just to entertain the HTTP requests in this application demo. And then based on the ingress, we have a KEDA specification that comes up next. So where, I'm just going to pause here for a bit. So we specify that min replica count is about 2, max replica count 1000, cooldown period 30 seconds, polling interval of 10 seconds. We are looking at the number of HTTP requests that hits the ingress, and specifically in a minute, we have a threshold of about 10, based on which we adjust the triggering every 30 seconds or so. So you can see KEDA helps to push along the replica set as it responds to the number of HTTP requests coming into your ingress. So now that we have seen the cluster and what is running, let's quickly get to the demo. So this is a Grafana chart powered by Azure Managed Prometheus behind the scenes. So what I want to bring your attention to is on the top left, you have the ingress graph. So as the traffic comes along there, so you'll see a bursty traffic being introduced by Azure load testing. So you'll see a spike in traffic here. To start off, there's only, as you can see, there's only one replica that's running in the cluster. We have like 4 nodes in NAP. So there's one default node, which is the user pool where we are running the workload, and 3 system nodes that NAP has decided. So at the start, that's what we have on offer. Then, so this is the node graph, and this is the replica graph that I mentioned. So here you have the, on the bottom right, you see the CPU requests for deployment and memory requests for deployment. And these are 2 things that is showcasing VPA in action. So let's see the node chart. You should see the node chart change as NAP adjusts the most optimized queue nodes in response to the traffic, and as the replica count increases in the bottom chart, which is all KEDA doing its thing. So next we'll see how as the traffic comes along, what happens. So we start with 0.1 and 50 megabytes as we put in our deployment. So you can see there's a spike. We're just getting the traffic started into the ingress. So around 650, there's a spike coming in, and soon we'll be monitoring the replicas in KEDA, and then as a consequence, what is happening on NAP as the number of nodes get optimized as well. So here I'm using a watch on KEDA. So you can see all this quickly in response to the traffic coming in. It's already scaled up with a replica set. And this is all a watch on what scaled object that we defined earlier. The same you can observe soon in the Grafana charts as well, which will go next. So there you go. You can see KEDA is already asking for all these pods, the new replicas, and then you can also see just above it on the node section, you can see there is one extra node that is getting provisioned, and already VPA started in action. It has changed the core request from 0.1 to 0.8. And the memory has spiked up from, in terms of requests, is moved from 50 to close to 400. So next we will see the load testing to completion. And with the fluctuation in the traffic, we should see how KEDA, NAP, and so basically here, I'll just check the new node that was created. So you can do a get node. Pick up one of the default nodes that was created. If you want to see what type of SKU goes into it, so you can just do a describe on that node. That's what we will be doing, and seeing the SKU returned back. It need not be the often used SKUs. So NAP will always try to bring up the most optimized one for cost and right sizing. So it's a SKU that has landed now on describe. And this can get consolidated as it move along. So basically here, you've seen the load testing completed after about 20 minutes. We ran it for about 20 minutes. And you can see that whatever you see on the ingress chart is reflected in both the replicas as well as in the node, as both NAP for nodes and KEDA on the replicas are trying to optimize consistently. And the same is seen with VPA as we adjust the requests on the CPU request and the memory request graph. So there's a small adjustment there on the memory request as well. So this is basically the demo to showcase, how you can bring some of the finer aspects of scaling together. KEDA for replicas, VPA on the adjusting memory and requests, and obviously NAP for node consolidation to settle on the most optimized SKU set. All right. So basically, I just want to summarize. Essentially, you can use KEDA for event-driven scaling. You have over 50 plus Scalers, VPA, like I said, helps adjust requests and limits by usage. HPA, horizontal pod autoscaling, looks at metrics like CPU memory, and you can increase or decrease replicas and pods accordingly. So that's in a nutshell what we saw in the demo as well. Something that we have recently introduced, we are happy to say that we have now 5,000 node support for AKS by default in GA. So the AKS control plane automatically responds to the load in your cluster and scales the control plane automatically. So you will get better performance at lower scale points and more reliability at high scale points up to 5,000 nodes and 200,000 pods. What about multi-tenancy? This is all about sharing infrastructure across tenants, teams, business units, and there are definitely multiple types and variants of multi-tenancy. Some of it we'll see here. Soft multi-tenancy comes in two forms. So one, we are talking about dedicated namespace here. So you can see a cluster is shared by many tenants, the namespace being the one logical boundary here. The pros here are higher pod density, good best bin packing. Infrastructure gets shared with less idle resources. It's not entirely safe for hostile environments, and obviously you need additional security measures if not all the tenants can be trusted here. The other model is to use dedicated node pool, soft multi-tenancy. This one again has one node pool per team. You can see there in the diagram. The pros being medium pod density. Can apply Azure tags to the node pool, and that propagates to the node and persists. Cons being request trust between tenants and policies such as RBAC, quotas, and network policies, some of which we saw earlier in the day. Hard multi-tenancy, where you're obviously taking the choice to go dedicated cluster per workload and team. The pros are easy isolation, cost allocation and chargeback is pretty straightforward. Best case for tenants that do not trust each other often from a security or resource sharing perspective. Cons being, obviously higher management and financial overhead, generally lower pod density and over provisioned resources. We talk about node scaling here. Obviously, I mentioned NAP, which is our most recent offering, node auto provisioning. But how many of you have used cluster autoscaler here? So I think most of you are familiar with it. So essentially, manual scaling, you have to do the bulk of the work in terms of knowing what SKU to provision your workloads on, and then what is the count of the nodes. And with cluster autoscaler, it gets slightly better, I would say, where you just need to know the SKU, and then it takes care of, if you specify a min and max, takes care of what is the requisite number of nodes any point of time. Scales up and scale down accordingly. With node auto provisioning, you go one step further, where you don't need to worry about the SKU or the numbers, and it's all automatically provisioned for best resource utilization as well as from a cost angle. I say cost angle again and again for this track because I can show from a test that we did. So what we did here is we were comparing the three scalars. We took a very simple 3-tier application. So you can see. Don't need to go through everything. So there's a middle tier application of 5 replicas, 10 vCPUs, 100 megabytes. There's a front end, 30 replica, 15 cores, 200 meg, and back end where we have about 10 replicas. That consists of has a request of about 20 cores and 2000 meg. So we kept this workload consistent on all the 3 scalars for the same time span, and let's just see the results. And something that you can do on your test or dev environment as well before taking the choice of what scalar suits your need. So we just went with the total request was coming around 50 cores and about 28 gig for the entire application. So as a newbie operator persona, you can probably take. We went with one of the commonly used SKU type, DS3V2, which has about, I think, 4 vCPUs and 14 gig, memory. So from a operator persona, if we went with 20 nodes of this particular SKU size, it was costing X amount over month. So this was the amount over month. But the key takeaway here is when we did the same thing, the exact same configuration on the exact same time span, on the same SKU, we just changed the scaling method from manual to a cluster autoscaler. We could see it was only utilizing about 80% of the total cost of manual scaling. And node auto provision did one better in terms of that. So the results were pretty good in terms of 35% of all it took for manual scaling, and approximately 44% of what the cluster autoscaler came up with. So this was some major findings where, from a cost angle, you can consider node auto provisioning, and it sort of simplifies the choice of SKU as well. So you can see the SKUs are vastly different, very different from what we ended up going with manual scaling. Then we'll move to infrastructure selection best practices. So here, few salient points. Spot, if you have a consumption of unutilized capacity and it's good for, you have workloads that can sustain certain interruptions, that would be a good bet. We have seen costs reduce up to like 90% with Spot. And we know that ARM-based compute instances for containerized workloads has more than doubled in recent years, and Ampere Alta ARM-based processors come into picture there. Capacity reservations is a feature that's now generally available. It helps to safeguard with allocation failures by pre-allocating capacity. And Azure Reservations offers up to like 72% discount compared to pay-as-you-go prices. So something to keep in mind. And the last point I want to mention is AKS now optimizes cube reserve memory by up to 20%, depending on your node configuration, and it is available with 1.29 in preview, and we are soon to go GA or generally available on 1.29 version by end of the month. Some best practices for dev test environments and clusters. Turning off clusters that need not run all the time helps to conserve computing and save on prices. All the objects in cluster state will be maintained when the cluster starts again. AKS also, as you know, comes with a free tier offering where the control plane is fully managed and free of charge. This is great, especially for small cluster scenarios. And for production workloads, you can definitely upgrade to the standard tier, which provides uptime SLA and guarantees up to 99.95% availability on the control plane. Spot node pools, we spoke about it, especially for unutilized capacity. It's great, and if you can withstand certain interruptions and evictions on the workload side, that is a good bet, especially on the testing and dev environments. On the storage side, for better utilization and cost efficiency, blob CSI storage makes more sense because it's cheaper than disk and file offerings. You can disable the AZ file and disk CSI drivers, which are turned on by default if they are not used for your scenarios. Azure Container Storage Preview with ephemeral disk provides local storage and helps get the best performance on no additional storage costs. You can pack multiple persistent volumes into a single disk here. And with that, I think I'll pass on to Kaysie. So we can also entertain some questions end of the session, or you can also approach us in any of the booths here. We'll be in KubeCon. So thank you. Pass to Kaysie.
Thanks, Karthik. All right, let's chat about visibility, why it's so important. Some interesting data. So a recent FinOps microsurvey put out by the CNCF actually showed that a lot of folks have no monitoring in place at all. Some folks are having some method of estimating, but only 19% have accurate methods for showback. Only 2%, which is very little, have a real chargeback program. So if we don't have visibility into costs, it makes it really hard to know where do we start optimizing? Are my costs expected, or is there some kind of event that has cost anomaly? Some other findings are customers are all across a spectrum in terms of where they are in their FinOps journey. Some are in the evaluation and analysis stage, 35%. Several are piloting or rolling out standardized toolings and processes, but 10% still have nothing. they haven't started thinking about cost optimization, but today will help you kind of start this journey. We have this feature, AKS Cost Analysis add-on, which is now generally available. It is a Azure native cost allocation and visibility tooling built directly into Portal UI so that your cost data broken down by Kubernetes constructs, so clusters, namespaces level, are all visible directly in Portal. This feature is also built on top of the Open Cost project, which is an open source, vendor-neutral CNCF sandbox project. We've partnered really closely with the community members and Open Cost team, and we're also contributing back to the team, which has been a really great partnership so far. In terms of monitoring and observability, we had a whole session right before lunch, so we know how critical and how important it is. But we also have to remember that there's this monitoring versus cost trade-off. So the more logs that you collect, the longer you have the data retained. This has cost implications to it. So there are a few different ways that you can optimize for cost within monitoring. First is optimizing for data ingestion. You can specify data collection frequency, tune it down from every minute to every 30 minutes, for example, if you don't need logs at the top of every minute. You can also include or exclude certain namespaces for log collection. And there's also cost optimized out-of-box presets, which help pre-configure some of these choices for you. Managed Prometheus is also a really good cost alternative to Container Insights, if that's something you're interested in. And then we also have transition to low-cost alternatives for verbose logs. The Container Insights has a schema for container logs specifically called Container Logs v2. This is compatible with basic logs, which are optimized to only collect the logs that you require. There's paid per paid querying of the data and reduced ingestion periods. So this is a great optimization capability as well. Now for GPUs, what's the story between GPUs and costs? With the AI boom, we all know that GPUs are a hot commodity and they can be very costly. In terms of utilization, so regardless of size or resource requirements for your workloads, by default, GPUs have exclusive GPU access. This means that a single workload will be exclusively accessible for one GPU on a node, but this also often leads to underutilization of the resources since oftentimes workloads don't require a single GPU access. You can partition and share GPUs through a few different methods. So MIGs, multi-instance GPUs. This allows you to partition and share GPUs across multiple workloads, essentially chunking up the GPU into mini GPU instances. You can partition up to 7 instances, and each is fully isolated with their own bandwidth, their own cores, memory. And for time slicing GPUs, this is another method where you can share a single GPU across multiple users. You can define a set of replicas for the GPU, and then each replica is handed out to an independent pod, so the workload will run on that kind of slice of the GPU. And you can also combine MIGs and time slicing. And for our demo, we'll show AKS Cost Analysis plus GPU time slicing. So I've pre-configured a cluster. It has 2 node pools, a default node pool with the standard DSV2 node, and then a regular GPU node. And then here I'll show creating the GPU time slicing node. So once this is created, it'll just take a minute. Then I'm going to install the NVIDIA operator. Once this is done, we should see the status change to deployed, specifically in the GPU operator namespace. Then we'll create a config map for the operator namespace. By default, time slicing is not applied to the GPU node in a cluster, so we have to apply a patch and set the right parameter so that time slicing is enabled for our GPU node. And then we'll check that our nodes are up and running. We have to add a label to the GPU node specifying we want 4 time slice partitions. So basically, our one GPU is chunked up into 4 instances. And here we're just verifying that the config map has propagated and everything is set up properly. We'll create a new namespace to run our application. We have just a single pod application that will be scheduled to the GPU operator time slice node pool. We'll apply the YAML file. And then we will add a watch to our pod. Like we can see our pod is up and running as expected. And we describe our node, we can see that the time slicing node, that we can see that our app is using one of the 4 GPU slices. So theoretically, we could actually fit 3 more of the equivalent workload on this GPU, and it wouldn't be requesting more usage, more CPUs, more memory. It'll execute on this node. And then if we pop over to Portal, we'll look at the cost data. So we're in the cost analysis view right now. And we go to the Kubernetes cluster overview. Here we see an overview of all our clusters across resource groups, regions in our subscription, the top level costs. You can specify a certain date range where you want to do show back or look back at the data. So we'll specify a particular day that we enable the time slicing capability. And if you drop down, this is like a bill of resources within the cluster. You can see all of your VMSS resources, your networking, your storage resources, how much was used versus idle versus reserved for system-related processes. You can also drill into the namespaces view. All of our application namespaces are here with their associated compute, network, and storage costs, as well as shared costs like idle, service, SLA, fee, and system charges. And then there's also the assets view. This is a categorical grouping of the resources within your cluster. And within compute, we can see that our regular GPU node pool and the cost of our time slice GPU node pool are more or less the same. The main call out here is that with time slicing, you can essentially run 4 of the equivalent applications on one GPU versus our regular GPU node, we could only run 1 application. So for that, if we were trying to run 4 applications, the cost would effectively quadruple. Now for multi-cluster. So far we've kind of been looking at a single cluster. What about fleet? If you have several hundreds of clusters, you know, it's all very difficult to manage them at scale. Upgrading, monitoring, creating resources can be a challenge. So fleet is basically a collection or grouping of AKS clusters. There's an agent cluster, a host cluster, and then 3 member clusters that are part of the fleet. Member clusters can be across any region, subscription. As long as they're in the same tenant, they can be joined to a fleet grouping. This is particularly valuable for infra teams that have to manage, scale, upgrade. And we also, for fleet, support rolling upgrades, resource propagation, and one of the new capabilities that we're introducing is fleet workload placement based on cost metrics. So we built this completely in open source. This capability is open source right now, so if you want to try it out, do go ahead. There are 3 new metrics that we've introduced. First, per resource unit costs. This is great for a scenario where I have a CPU-intensive workload. I want to schedule it to a cluster with the cheapest CPU resources. You can do the same for memory. The second metric is allocatable and available resources. For example, if I have a cluster that is memory intensive, I want to schedule it to the cluster that has most available memory. And then lastly, number of nodes. This is for scenarios where I want to balance the resource usage across my clusters. I want to eliminate hotspots so that not one cluster in particular is getting overloaded. And let's take a look at what this looks like in a demo as well. So for this demo, I have 1 hub cluster and 3 member clusters set up. The member clusters all have different VM sizes, and they have cluster autoscaler enabled. So I'll check on my hub cluster first, hub admin, and then I'll look at my 3 member clusters. So Brave Lion, Jumping Cat, and Smartfish. Oops. The demo does not want to cooperate. Let's try again. There we go. All right. So we're checking my hub cluster, and then I'll check my 3 member clusters. And then I'm going to set a watch so that I kind of get a dashboard of all of my metrics, and I'll see how they change as I schedule through the different 3 scenarios. So node cost, CPU memory cost, allocatable, and available for both CPU and memory. For my first scenario, I have 3 replica application. I want to schedule it to the cluster with the cheapest CPU cost. So based on the above dashboard, I would suspect it would be scheduled to Brave Lion. I'll make some changes to the cluster resource placement API, which helps place resources based on cluster affinity terms and topology spread constraints. So there we see cluster 1 got scheduled. For scenario 2, I have a 1 replica workload that's memory intensive. I want to schedule it to the cluster with most available memory and with at least 16 gigabytes available. So either Jumping Cat or Starfish would satisfy those constraints. Let's see which one it picks. It chose Smartfish, and we can see available CPU and memory had changed after it got scheduled. And then for my final scenario, I now have a 10 replica app that I've specified 2 scheduling conditions. So first, I want to pick the cluster with the smallest amount of nodes, and I want to choose the cluster with the lowest CPU cost. So looking at our dashboard above, it'll most likely choose Brave Lion because all of the node counts are the same across clusters, so that condition is not satisfied, and then we'll look at cost. So there we go. We can see all the metrics have changed after the workload was scheduled. Now expanding beyond Kubernetes into the broader Azure ecosystem. There are additional discounts that you can leverage for your environment, particularly savings plans and reserved instances. They're both 1 to 3 year upfront commitment terms that offer fairly good cost savings as compared to pay-as-you-go. Reserved instances are best for stable workloads, so if you have workloads consistently running that have the same SKU, same region, you don't expect any changes there, reserved instances are the great discount plan. Savings plans are a bit more flexible if you have resources in different regions or SKUs, but you have a consistently hourly spend. That is probably a better option. And then Azure Hybrid benefits, this allows you to apply your on-prem server, Windows Server, or standard licenses with software assurance to pay for your AKS resources. And FinOps. We're starting to see more and more companies having dedicated FinOps teams. Was able to chat with some of you during lunch that do have dedicated FinOps teams, which is great. FinOps is the intersection of people from finance, engineering, operations, all working together collectively to increase accountability of cloud costs across teams, to take action together, to be more cost efficient. And controlling costs is not a one and done process. It's a continuous optimization that should be revisited. And would recommend checking out the FinOps Foundation. Microsoft is one of the premier members of it. And the FinOps Foundation actually puts out their own conferences similar to KubeCon. It's called FinOps X. I think it runs 1 or 2 per year now, but that's also a great opportunity for FinOps practitioners to knowledge share or just learn more about FinOps in general. And then finally, our cost and sustainability. It wouldn't be right to kind of talk about cost without talking about the impacts of sustainability too. They're very interwoven, as the more you can reduce your infrastructure and cloud wastage, it helps your cost and your bottom line, but it also helps to minimize your carbon footprint. So this is an area that we're really excited to continue exploring in upcoming months. But if there are particular sustainability scenarios that you have in mind, would certainly love to chat with you after. And finally, our key takeaways. So a lot of best practices were shared, but if there are 2 things that we would want you to try is Node Auto Provisioner and AKS Cost Analysis. These 2 are game changer with reducing the operation overhead and auto provisioning SKUs to meet your workload demands. And then also just getting visibility so you know what needs optimization. With that, thank you so much. Enjoy the rest of the session.